Hey, hi everyone, and welcome to 024F. And for this video and the succeeding videos, I will discuss the different method of solution for solving system of equations. So we are not limiting ourselves to system of linear equations, but we also have the systems of equations in general. So for the intended learning outcomes, we want to be able to, for this first part, we want to be able to discuss the direct methods. So we want to solve the system of linear equations using the Gaussian and the Gauss-Jordan elimination. And then we will also discuss this LU decomposition. And then we will compare their advantages and disadvantages within these direct methods. So for the outline, we will only discuss here the direct methods, which are the Gaussian elimination, Gauss-Jordan elimination, the LU decomposition, and their comparative efficiencies. So for additional review, you can access this PDF in our LMS. Okay, so let's jump into the direct methods. So for the direct methods, we have already discussed this in your linear algebra class, wherein we discussed the different ways of solving system linear equations, such as with the use of Gauss elimination, Gauss-Jordan elimination, the LU decomposition. So LU decomposition actually has different types of decomposition, but we will only utilize the Doolittle's method. And then we know that we can also use the inverse method and also the Cramer's rule. So again, for this course, I will only discuss the Gauss elimination, Gauss-Jordan, and the Doolittle's method of LU decomposition. So in comparison to the direct methods, we can also utilize an iterative way to solve this. So iterative methods, indirect methods, or numerical methods, we can use these terms alternatively to describe the approximation of our solution. So it usually has also an initial value, initial guess, and it could be refined using this iterative algorithm. So this can be utilized for matrices or system of equations that has more than 100 unknowns. Okay, or one of the number of unknowns and also the number of equations. So why is that? So we will discuss this a little bit later with regards to the rounding error. So when the equation is too large, usually the operations in the direct methods will be a problem. So it will be an exponential error as it changes or as it transfers over time. So we have three different iterative methods here: the Jacobi method, the Gauss-Seidel, and the relaxation methods. To be specific, the successive over relaxation. So what is the difference between these two? So for direct method, we have a fixed number of operations that we utilize, okay, depending on the method. So in Gaussian elimination, we can use only 3 elementary row operations to solve a 3 by 3 matrix, and so on. So we already know how many operations we should use. But for iterative methods, we usually have an initial solution and there will be a convergence. So it will be again an iterative procedure. So for the first direct method, we will discuss here the Gaussian elimination. So we are already familiar with the Gaussian elimination at this point. And how do we do this? So we have this system of linear equations notated in this form. And we want to change or manipulate this equation in a way that we can solve it. So we usually remove the lower triangular coefficients and then perform the back substitution. So we call this form in Gaussian elimination, the final form of Gaussian elimination, to be called the row echelon form. So the first thing, so the very basic way of solving a system of linear equation using Gaussian elimination is using the naive Gaussian elimination. So this is what we have learned before in our linear algebra class. So usually, we just perform these operations to make this lower triangular zero, and well, most of the time we will not be, we don't need to interchange the rows, no, for most of the time. Okay, so for naive Gaussian elimination, the problem here lies when the matrix has a zero in the diagonal. So we can remedy that later using a different or a variation of this naive Gaussian elimination. So um, so the algorithm for solving this matrix using Gaussian elimination can be seen here. Although it will be a little bit too much, no, to understand this, that is why I will just demonstrate how this algorithm is used. So this algorithm here can be utilized for computer implementation, for programming. So again, no, naive Gaussian elimination can encounter problems such as dividing by zero and sometimes precision problems through these operations. So the problem again, no, if we have, let's say, a matrix, and if your first term is zero here, so you cannot solve this using the naive Gauss elimination. But if we utilize an exchange of rows, we can solve this in an even better way, no? Or we can actually solve this matrix. So that exchanging of rows is called the partial pivoting. So we can improve the solution of our Gaussian elimination through the following strategies. So we can utilize higher precision, we can utilize partial or complete pivoting. So we will only discuss partial pivoting, and then we can also scale the value. So we will not discuss this at this point. No, I think so this might be a part in the future, but for now, there will be scaling values in this assessment tasks. So for an example, no, we can improve the naive Gaussian elimination by using partial pivoting. So we can exchange the rows, we can exchange the rows and columns. So for partial pivoting, so rows, complete pivoting, we can use or we can exchange the rows and subsequently the columns as well. So we have an example here, and we want to solve this using the naive Gaussian elimination and Gaussian elimination with partial pivoting. So use for decimal places. Okay, so we have this problem. How do we solve this? So the goal for Gaussian elimination is to arrive at its row echelon form. But for naive Gaussian elimination, we can just go directly to this first column and then make this 0, and then move on to the next column, make this 0, and so on. So we only have 3 elements in the matrix that we want to make to make 0, no? So what should we do here? So we have an operation, we have, to review, no? We have 3 different elementary row operations. So the first elementary operation, so EO1, this is the exchanging of rows. So we can exchange row I and row J. Actually, we do not have a hat here. And then for elementary operation 2, we can add, or we can multiply a row by a non-zero constant. So we have alpha, okay, where alpha should not be equal to 0. And then the third elementary row operation, we have to add a multiple of another row. So we have Ri plus alpha Rj. Okay. So what are Ri here and Rj? So Ri means the current row. Okay, and then the J is the reference row. Okay, so remember that. And when performing when performing Gaussian elimination, we want to make this 0, and the way to find or the way to solve this is we will utilize only this third row operation, which is that a multiple of a row. And the alpha that we should use here actually also has a formula. So for the alpha, this is equal to the negative of Ri, or is it Ri? Negative Ri over Rj. Um, yes, negative Ri over Rj. Okay, so let's perform this elementary row operation. Let's solve it. So for the first column, we can actually solve this simultaneously. So we have R2, so we are operating on row 2. So row 2 is now equal to row 2 plus alpha and then R. So the reference row here will be the first row. So why the first row? Because the first row will be unchanged. And usually we have the reference, we usually reference the diagonals, no? So this is the first element of this diagonal. So we will utilize this value as our, or this row to be exact, for our reference row. So we have R1, R1. And what should be alpha? So alpha here will be the division between these two. So we have, this is equal to, so alpha here will be negative, no? So since this is negative, so we have negative, let's make this blue. So negative Ri, 0. I think I'll move this. So 0.194, 0194, all over 0.0286, and then R1. Okay, so this is the operation for the first row. For the second row, we can also utilize this row, no? So we have row 3. We want to make this 0, so row 3 plus alpha and then Rj. So Rj here, the reference row here will be the first row as well. So we have R1, and then the alpha will be negative current over reference. So this will be negative 0.333 all over 0.0286. Ayan. Okay, so the new matrix here will become, okay, so copy the first row, since we are not operating on the first row, no? Okay, so create an augmented matrix. So for the first entry here, first column, we have this equation to represent this problem. So what we will do here is just create an equation to make things faster. So we have, let's say, alpha A minus, we have 0.0194 all over 0.0286 multiplied by B, so times B, alpha B, and then calc. So A here will be R2, B here will be R1. So A is, again, R2, so N is this 0.0194, and then 0.0286. So as we can see here, this will be 0, no? So meaning the add a multiple of another row operation made this 0, this first entry. So for the second entry, we will now utilize this one, no? Okay, so let's do this again. So negative 0.02291, and then 0.019. So we have negative 0.042. Okay, and then what's next? So we have 1 and 1, and so on. No? So we will continue this. So 1, 1. So the value here will be 0.3217, and then for the last entry, we have 0.952 and 0.991. So the answer is 2.2798. All right, and then for the second row, so calc and then 0.333. So sorry, we have a new formula pala, no? So for the new formula, so for the third row, we have a different equation to represent this operation. So we have to just change this to 0.333. Okay, so calc and then again 0.33, and then 0.0286. So 0 again, no? This just confirms that we are correct. And then we have 0.333 and then 0.019. So this is 0.1118. Okay. And the next one we have 1 and 1. So negative 10.6434. And then last, so we have 1 and 0.991. So this negative 10.5386. Ayan. 5386. Okay. So what's the next one here? So the goal here again is to make this the reduced row. The row actually form only. So we want to make this 0. So we have to make this 0 as well. And also we are on this portion already. So we want to make this 0 now. No? So what should we do here? Now we will perform again the operation. So we have the current row, which is the third row. No? So this is the first, the second, and the third row. Okay. So the third row will be equal to R3 plus alpha. And what should be the reference row? So we can choose either we can choose row 1 or row 2, but the correct one, it should be row 2, because if we utilize row 1, as you can see, we will have a new value here. Ano? So to prevent this from happening, it might not be 0 again. So we want to operate this again with a term that has a 0 already. So we want to utilize this. And usually that is the diagonal. No? So we transfers to this. Okay, so we have R2, and then the alpha will be, so the alpha will be the ratio of these two. So the negative ratio of these two, so negative 0.1118, and then over negative 0.042. As you can see, we can cancel out the sign, so this will become positive. And then row 2 as our reference. Okay, so perform this operation again. We have a new equation. We have 0.118, 1118, 1118, 0.042. So this will be negative 1. Oh, sorry. It should be different, no? So, sorry, we did not input pala, no? So, we did not input the values yet, so we have to input the value. So, we have 0.1118 and negative 0.04. Oh, what's wrong? Oh, this should be positive. Okay. So, calc, and then, okay, so this will become 0. So what should we write here? We can just copy paste the first two columns, first two rows. 0.0190, 1.00, and then 0.991. 0, negative 0.042, 0.3217, 0.2798. And then we have 0 here. Actually, you can operate this now. So 0 plus 0 will still be 0. And then this one will be 0 again. And for the next operation, we have to calculate this too. So negative 10.6434. 646434. And then 0.3217. Okay, is that right? Check. Okay. So we have negative 9. Negative 9.7871. Okay, and then for the last one, we have negative 10.5386, and then 0.2798. So negative 9.79. Okay, negative 9.79. 3 pa pala. 3. Ayan. Okay, so what's the final step here? We have to perform the back substitution. So the back substitution, basically, we want to solve this again by creating this or making this again, sorry, making this again the system of linear equation. Now, we will convert this again into a system of linear equation form. So this will be 0.0286. We have x1 plus 0.0190, x2 plus 1.00, x3 is equal to 0.991. We have negative 0.042, x2, and then 0.3217, x3 is equal to 0.2798. And then the last one, we have negative 9.7871, x3, negative 9.7938. So to solve for x3, we can utilize this. So therefore, the final answer for x3, so x3 will be equal to, okay, let's write this down again now. 38 over negative 9.7871. So for x3, the division of these two variables, equations, is two values, negative 9.7938 over negative 9.7871. We have 1.0007, 0007, okay, for x3, and then for x2, here, we can now utilize this second equation. We can substitute this x3 here to get x2. So this will be equal to, so I'll just skip to the manipulation, no? So 0.2798. So this will become negative. So negative 0.3217. So x3 is 1.007. 0007. Then all over. So we have the coefficient of negative 0.0, negative 0.0420. So for x2, that will be equal to, okay, so we have 0.2798 minus 0.3217 times 1.0007, negative 0.0428. So the answer for x2, we have 1.0030. Okay, so this will be your answer for x2. And then for x1, we can now utilize this last one. So we can solve for x1 by substituting x2 and x3. So x1, therefore, this will be equal to 0.991 minus, okay, so we have 0.019 x2. So x2 here, we have 1.003, okay, and then minus 1 times x3, which is 1.007, okay, and then all over. So the coefficient is 0.0286. So x1 will be equal to, calculate 0.991 minus 0.019 and 1.000, and then minus 1.000 all over 0.0286. So the answer for x1 will be negative 1.0055. Negative 1.0055. Okay, so this will be your final answer. Okay, that is for the naive Gaussian elimination. How do we now solve this using the Gaussian elimination with partial pivoting? So with partial pivoting, sige, let's write this down again. Yeah, let's write this down again. 0.0286, 0.0191, and then augment this already. Okay, and then we have 0.0194, negative 0.0291, 1, 0.952, 0.833, and 1.60. Okay, so for the Gaussian elimination with partial pivoting, so the thing here is when we are solving for the first column, ano, we want to choose from these three rows, which of these three rows has the highest absolute value. So the highest absolute value in this first column to be chosen as the first row will be this 0.33. So if we will utilize Gaussian elimination with partial pivoting, we want to swap these two rows. So the new system of equations will be this. Okay, 0.00. Then 0.0194. So retain the second row. And then the first column will now be the third. Sorry, the first row will now be the third row. Okay, so this is the partial pivoting. We are exchanging the rows to prioritize the highest value per column, no, when performing Gaussian elimination. So the first elementary operation we should utilize is this for the second row and this third row. So for the second row, we have R2 that is equal to R2. Okay, I'll just write this down. So we have negative 0.0194 all over 0.333, and then we have R1. And then for R3, we have R3 minus, so we have 0.0286 all over 0.333, and then R1. So the new matrix here, okay, will now be, we copy paste the first row. Okay, we will now perform the operations after this one. A1. Alright. So for the formula, we have R2, so A minus 0.0194, and then 0.333, and then alpha B. So substitute the values here for the first, for the second row and the first row. We have 0.0194. Just check now if this will become 0. Okay, and then 0.33. So this is a 0, no? And then for the next one, we have calc negative 0.09291 and 0.333. Okay, and then this will be negative 0.0485. 485. And then we have 1 and 1, 1, 1. So 0.947, 417, and then 0.952 and 1. 0.8937. Okay. So what's next? So for the third row, we have a new formula. So let's just change this. This 2.0286. So so the first column, no? So the rows of the first column. So 0.0286 and 0.333. 0.0286 and 333. So 0, and then again, sorry. And then again we have 0.019 and 0.333, negative 0.0096. 0.9141, 9141, and then last one, so 0.991 and 1. So 0.9051. Okay. So for the next step, no, we want to change this again to its row echelon form. So okay, we are checking now for this two columns or two rows. So since this already has the highest absolute value, okay, we are already good with that. We can just perform the operation again. So we have negative, sorry, we have to write the row operation. So we have row 3 minus negative 0.0096 all over negative 0.0485. So we can cancel this, no? We can cancel this one. So this will just be negative. So the new matrix here will now be, so we have okay, we have to use a different formula. So 0.0485 and 0.00, it's 0.0096, negative 0.0485. So 0, okay. So this will be 0, this will be also 0. And then for the next one, we have 0.9141 and 0.9417. So we have 0.727, 7, so 7, 0.7277, and then the last entry 0.9051, 0.8937. So 0.7282, 7288. So I'll just copy everything, no, from this first and second rows. Okay, so how do we solve this now? So as you can see now, we have a pattern here, ano? As we can see, what we are doing here now, we have a pattern here that when solving for a row, solving the solution of a row, we're just dividing this, no, by this. And then for this second one, we are just transposing this to the other side and then dividing this by this, no? So to solve for the first variable, no, x3, using back substitution, this will be just the division of these two numbers. So we have 0.7282 and 7277. 7277. So x3, so calc point, sorry, not calc, but 0.7282 and 0.7277. So 1.0007, 0007. Okay, we have the similar solution for x3. For x2, so what will be the solution for x2? So the x2 here, this will be equal to, so always write the constant on the rightmost side, and then this will become negative, so negative 0.9417 multiplied by x3, so x3 here will be 1.0007, and then all over, so the coefficient here, no, so this is what we are looking at, divided by this negative 0.0485. Okay, so what is the solution? Uh, 1.033. 1.0033. Okay, so we have okay, we have a different solution, no? As you can see. Okay, and then for x3, sorry, x1, that will be equal to, so we will utilize this row. Okay, so we have 1 minus 0.333 multiplied by x2, so 1.0033, and then minus 1 times, we have 1.0007, and then all over, divide this by 0.33. So x1 here will be, we have but we have 1 minus 0.333 times 1.0033 minus 1. Actually, I will just solve this one directly, and then 0.333. So the answer here is negative 1.0054. Okay. And so this will be your final answer for the pivoting or Gaussian elimination with partial pivoting. Okay, so again, to summarize, the difference between the naive Gaussian elimination and the Gaussian elimination with partial pivoting is that in partial pivoting, we are exchanging the rows depending on the column that we are operating in. So we want to have this reference as the highest number or the largest number compared to this one. So the absolute value, the largest absolute value should be this this diagonal, no? Okay. So we can also solve our system using the Gauss-Jordan elimination. So instead of the row echelon form, we can utilize the reduced row echelon form. So in this portion, we will just perform more elementary operations and we will not utilize back substitution. So going back again, also we have this problem. Let's say you want to continue this problem. Okay, we can either use a naive Gaussian elimination or a Gaussian elimination with partial pivoting to continue Gauss-Jordan elimination. And for this portion, I'll just utilize this Gaussian elimination with partial pivoting, this portion here. So the next step here to make this the reduced row echelon form is to make this one, okay, make this one and then make this zeros. Okay, so I will just copy this. Okay, sorry, there's a lot of copying that we will do. I think I'll just copy. I cannot copy this. Yeah, let me just draw this again. Okay, sige. 0.333, 111. Okay. Let's do this one by one. So we have 0.333 and then 0.333, 1 and 1. So for the second row, negative 0.045, 9417, and I forgot the last one, 8937. And then for the last row, 0.7277, 0.728. Okay, so for Gauss-Jordan elimination, the next step now, after Gaussian elimination, we should make this diagonals into 0, or we should change this diagonals into zeros. So for this first part, as you can see, we can divide this by. So we can do this simultaneously. So for row 1, multiply this by 1 over 0.333. And then for row 2, divide this by 1 over negative 0.0485. Okay, and then for row 3, this will be 1 over 0.7277. Okay, so we have row 3. So the new the new matrix will be, so 1 over 0.33. So I'll just substitute here E. So calc everything. So this will be 1. This will also be 1. And then we have 1. Okay, so this is 1, 1, and then 3.003. No? Okay, and then this will also be 3.003. Okay, for the next row. Okay. Negative 0.0485. Negative 20. So 0 and up. Should it be? Should be 1, right? Oh, so we did not substitute yet, no? So 0.9417. So I'll just skip through some of these problems. Okay, so we have 19, negative 19.4165. Okay, this will be 1. And then 0.8937. So negative 18.4268. Yeah. And then 0 and 0 here. So this will be 1. And then divide this by, so 0.7282 over 0.7277. So 1.0007. Okay, so for the Gauss-Jordan elimination, so what should we do here? This is similar to what we've done last time, but in a flip form. No? So if the Gaussian elimination, so we have this pattern, no? For Gauss-Jordan elimination, we start here, and then here, and so on. No? If we have remaining columns. So for this and this, we can do this simultaneously. So for row 2, okay, so for row 2, we have row 2 minus, okay, minus negative 19.4165 all over. So the reference row here will be 1, so over 1. So this will be just plus 19 plus 19.4165 R1. Sorry, R3. Okay, R3. Yeah. So I guess I'll have to write the first row first. So R1 and then R1. Sorry, I forgot about this. So this will be minus 3.003 over 1, right? And then row 3. Okay, so yeah. So for row 2, we have again A plus 19.4165. And then calc. Okay, we have the first one that we should compare now, this one and this one. So actually this is 0, 0, so 0 lang. And then 0 and 1. So actually this will still be 0. Sorry, this will be 1. You substitute this. But we can just focus on this portion also. This will remain unchanged in Gauss-Jordan elimination as long as you know what you're doing. So this will be, let's just check this out now. So negative 19.4165 and 1. Oh, sorry. Where's that? Oh, where's it? Ah, okay. So I forgot to put the B here. Okay, and then B is what? So 0, okay. So copying this first. So this will be 0, 1, and this will also be 0. And then for the last entry of this row, we have negative 18.4268. And then 1.007. So 0007. So we have 1.0033. Okay. And then for the last row, okay, we have this operation. So what should we do? So we have to change this. Actually, we will change this now. Everything else will change here. Okay, let's change the calculation. So A minus 3.003. We have 3.003. So calc, and we have 3.003 and 1. So just check if this will be 0 now. So this will be 0. Oh, so this one. Okay. And actually, you should start with the first column here. So we have 1 minus 0. So this will be just 1. We have 1 minus 3 times 0. So this will still be 1. Okay, it will remain unchanged. And then for this portion, we have 3.003 and 1.0007. We have negative 0.0021. Wait for the last elementary row operation. We want to make this 0. So we have R1, and the reference will be row 2. So we have minus row 2. Okay. So I can calculate this directly, So we have to copy paste this first pala. 1.0033, 001, 1.0007. Okay, so we have R1 minus R2. So this will be just 1. So 1 minus 1, 0. 0 minus 0, 0. And then negative 0.021 minus 1.033. That will be negative 1.0054. Okay, so what is the solution here? So we can say here that the solution here will be negative 1.0054, 1.0033, and then 1.0007. So this is your x1, this is your x2, and this is your x3. Okay, so that will be all for Gaussian elimination and Gauss-Jordan elimination. Thank you guys.